I'm Tetsuya Hoshino, Assistant Professor at the University of Tokyo. This talk is for beginners to intermediate users and is about trying GPU porting with DO CONCURRENT in Fortran standard. I would like to introduce Japanese situation about GPU environment. In recent years, many universities have installed GPU supercomputers. At the University of Tokyo, we are operating Wisteria VDEC. The majority of this supercomputer is a group of nodes equipped with S64FX, same as Fugaku supercomputer. But some are equipped with NVIDIA A100 GPUs. And JCA HPC, which is joint center of the University of Tokyo and the University of Tsukuba, will start operating OFP2 in 2024, and it will be a GPU supercomputer with more than 100 petaflops. As for Japanese applications, 80% of applications are written in Fortran and optimized for multi-core CPU-based supercomputers such as K and Fugaku. So therefore, porting of Fortran application to the GPU is a very big challenge in Japan. So there are several GPU porting methods for Fortran programs. CUDA Fortran is a language extension that can get the maximum performance of NVIDIA GPUs. It is currently only available for NVIDIA GPUs. AMD plans to provide HIP Fortran, but it is still under development. OpenACC and OpenMP are devoted to GPUs simply by inserting directives. However, OpenACC is only supported, in fact, by the NVIDIA compiler. So OpenMP for GPUs is also supported by AMD, but not all directives are available. So on the other hand, DO CONCURRENT is a language standard feature, so it is expected to be long supported in a variety of environments. So therefore, this study will evaluate DO CONCURRENT. So DO CONCURRENT has been supported since Fortran 2008, and the DO CONCURRENT applied can be executed in parallel. The right figure shows OpenMP implementation, so fit parallelize same loop. So DO CONCURRENT is very simple, but there is major limitation in the specification. It is not possible to call non-pure functions from the parallel region. Also, the Fortran 2018 specification does not support reduction or atomic operations. However, these are being considered for support in the next specification. And here is comparison of the implementation of DO CONCURRENT in the NVIDIA compiler with OpenMP 5.0, target loop, and OpenACC and CUDA Fortran. While OpenMP has target teams distributed parallel to, in addition to the target loop directive. So we compare DO CONCURRENT to target loop because target loop is more advantage for execution on both CPUs and GPUs. So first, DO CONCURRENT relies on the GPU's unified memory function for data transfer between CPU and the GPU. So therefore, there is no way to avoid the disadvantage of unified memory, such as lack of GPU direct communication. So the call of pure function, which should be possible according to the specification, is not possible in Fortran 2020.5. So on the other hand, it is possible to parallelize reduction loop, which is not in the specification. As a major difference from OpenACC and others, that number of threads can be changed, and asynchronous stream execution is not possible. To evaluate DO CONCURRENT, 3 applications were implemented and compared to OpenACC and OpenMP. So also, DO CONCURRENT can be executed on both CPU and GPU, so we evaluate it on CPU as well. And implementation costs were evaluated in terms of the number of directives and clauses to be inserted. So for example, in the case of this figure, the data directive and the copy in and copy out clause counted as 3 lines. However, we did not count the number of lines to avoid the concurrent limitation. So this is because changing the algorithm to avoid atomics, for example, is more difficult than changing the number of lines. For the evaluation, we used Rake GPUs and A100 GPUs on with area Aquarius node. So internode GPUs are connected by NVLink 3, and internode GPUs connected by InfiniBand HDR. For execution in Rake CPU, we use iFort compiler and nvfortran compiler. For execution on the A100, nvfortran is used as the compiler. So the options listed in the below. In the nvfortran compiler, we can switch between CPU and GPU by specifying a multi-core or GPU. And the managed flag is given when using unified memory. So the default is managed when do concurrent is used. The first application is ICCG solver. This is used as a linear solver in finite volume methods. In this application, it is important to note that 3 reductions are required in a single iteration. Reduction is not supported in do concurrent of the Fortran 2018 specification. So this is the result of the ICCG solver. The left graph shows flops using one A100 GPU. And the right graph shows the flops using single Ice Lake socket. The Ice Lake results further divided into 2 cases. The left is nvfortran, and the right is iFort results. The table above shows implementation and the number of lines, so corresponding to each bar in this graph. In the GPU results, the low performance of the leftmost STD per 1 is due to the reduction loops executed on 1-core CPU. So the implementation using unified memory, STD per 2, OMP GPU 1, and ACC 1 have similar performance. Looking at the number of lines modified, it seems that the cost performance of STD part 2 is better than OpenACC and OpenMP. So, and the fastest GPU execution is the OpenACC implementation using the async clause. But performance is degraded by the async clause in CPU execution. The implementation with OMP target loop has considerably degraded performance during CPU execution. So the performance of STD part 2 is not so bad compared to normal OpenMP implementation. But unfortunately, STD part 2 is very slow compared to regular OpenMP when compiled with iFort compiler. So the next case is H-matrix vector multiplication. The important thing is the H-matrix vector multiplication involves a lot of submatrix division weight. So it requires a lot of reductions. And the reference implementation also uses atomic add operation. So this is the result of the H-matrix vector multiplication. As before, the left side shows the result of A100 and the right side shows the result of Ice Lake. So the implementation in the table above is almost same, but STD do concurrent version has changed the algorithm, and this is not counted in the number of lines. In the leftmost STD per 1, since the innermost loop that should be parallelized is a reduction, only the outermost loop is parallelized by do concurrent. And the reduction loop is so executed sequentially. Therefore, it is very slow. So although STD part 2 has comparable performance to OpenACC, so it is more expensive to implement because the algorithm has been modified to avoid using atomic operation. And it seems that the combination of target loop and atomic operation in OpenMP seems not good. So on the CPU execution results shows that the concurrent outperformed OpenACC CPU execution. But this performance was only half as good as the regular OpenMP implementation. And the last case is 7-point stencil. This is a calculation pattern that often appears in fluid simulations. So this implementation overlaps the hello exchange communication and the calculation. So this is the result of 7-point stencil on multi-GPUs. The graph shows the result of strong scaling. The implementation using unified memory, so STD power 1, OMP GPU 1, and ACC 1 show similar performance. So this is because GPU direct RDMA is not available with unified memory. And the concurrent cannot avoid unified memory disadvantage. On the other hand, in ACC2 case, the async clause almost completely hides the computation and the communication. So this gap is GPU direct and async clause. So this is a summary of this presentation. We implemented 3 applications to evaluate do concurrent and compare them to OpenACC and OpenMP.